Alright, so let's talk a little bit about perimeters, areas, and volumes. So these are very important for certification exams, especially I would say volumes is what I've seen the most of. So very simply, a perimeter is just the length that you would measure or the distance you would measure as you walk around the outside of some object. And they can be regular or irregular. Basically, it's just this length plus this length plus this length plus this length, any number of lengths. So you can have any amount of shapes that you want, and they're very easy to calculate because it's just a straight addition problem. If you're measuring with centimeters and meters, then it's just something like 10.2 or 112.34 or something like that. You wouldn't be as precise as that probably. If you're measuring with feet and inches, then you could convert the inches into decimals pretty easily by dividing by 12. Then you'd have a fraction of a foot. So perimeters are pretty simple. So if this was 10 feet, then you know that the perimeter is 40 feet because this is square. If it is rectangular, you know that this is 2 feet, and you know this also is 2 feet. It might not be given. And if you know that it's to scale, then you could measure this out. Perhaps it's 1, 2, 3, 4, 5, 6. Let's just say it's maybe 13 feet. So 13 and 13 would be 26, plus another 2 and 2 is 26 plus 4, 30. So you'd have a perimeter of 30. Now the problem is that perimeters on their own are not as useful sometimes as areas which lead to volume, because a lot of times we're talking about fluid flow, whether clean water or dirty water flow. So when we're looking at area, you want to make sure that you don't confuse that with perimeter. A lot of times people will actually be trying to find an area, which is literally how much flat space an object takes up, and they'll instead add the edges together and think that that's what they have found. Or if you have maybe a cylinder, as with a pipe, whether it's flat, right, ovoid, or perfectly circular, people will mistake the equation for finding the circumference versus finding the actual area. So we want to be more concerned about the flow through this than what the actual circumference is, although that can be useful, especially when you're thinking about sizing of a project. So in this case, the perimeter, or the circumference, would be 2 times pi, which is 3.14 approximately, times the radius. So we have a diameter. Okay, we have a diameter, and the radius is just going to be half of that. Okay. So there's our radius r. And you can see it's a radius because it radiates out from the center. That makes some sense, right? Like a spoke. So if this has a fluid taking up approximately the bottom half of it, and we could figure that out with a sensor, or we could set that up based off of flow rates, then we're really interested in this area here. Well, the area of the overall circle cut in half would be a good approximation for that. And the area is going to be pi r squared. So there's our pi, which is approximately 3.14 unitless. And then the radius squared. So you can plug that in, whether that's in feet, meters, inches, whatever. As long as you're using the same units throughout your problem, you're fine. And you want to make sure also that you don't forget that in the end you're going to divide this whole thing by 2 if that's your approximation. A lot of times, if you have a square trough or something similar, then you are going to just have a very simple calculation. you take an approximation of some height, and this would be your new height, and this is your width still. So we can call that length if you want. A lot of people have memorized it as length times width. It doesn't really matter which is which. But the area here is going to be length times width, or height times width, whatever you'd like. It's just two-dimensional. It doesn't really matter what you call it, as long as you get the dimensions correct. So you might know a fraction. So this could be 1/3 of the overall available height. Now squares are nice and circles are nice, but a lot of times you'll have something a little bit different. You'd have a trapezoid. And maybe it's open. Could be open to the environment, and that's fine. So all you have to do is realize that either this is a trapezoid because there's an area equation for that, or you can take the area of a single triangle, another single triangle, and a square. I would just prefer to use the area of a trapezoid. You have a base, another base, and the overall height, and then you can figure out exactly how high that trapezoid actually is. So is it up to here? Is this the second base? Is this the second base? Is this the second base? Again, the big challenge is identify what shape, what geometric shape best identifies, or best approximates rather, your physical scenario, and then you use that geometry to figure out the area, because area really is going to show you the flow rate. It's what we call a flux. You're passing through an area. So same thing happens with light, same thing happens with air movement. Any fluid is just another type of movement through an area. And we get into volume. So let's figure that out. We'll go and explore some 3D shapes and show what this looks like. So a sphere is one type. Go into a 3D view. Nah, it doesn't really help. So a sphere is one type, and you can see that it still has a radius, and you can look at it from multiple directions, but you're not really going to find much of a sphere in terms of piping and other types of fluid flow scenarios. So cylinder is much more common, and you might have a cylinder that is, there we are, a little irregularly shaped, but that's still a cylinder. And a cylinder actually has a very simple volume calculation. So this is the area, and we know that the area is just going to be pi r squared. Again, there's our radius. If it's the diameter that you know, then all you have to do is cut that in half first, so it becomes pi times half the diameter, then squared, or multiplied by itself. And then we have the height, or if you want, it's the length of the pipe. Doesn't matter what shape it's in, really has some marginal effect, but as long as you don't have too many bends in there, then your approximations are going to be fine. So the volume becomes the area times the height. It's literally taking this area here and adding it up so many times across that height. It's really a calculus problem, but we don't have to think about it that way. And then you can just imagine that you're taking that area of water infinitesimally, there we go, thin, and you're just translating it through a certain height. You're making it flow through that pipe, literally. And you could have pipes where you have to take into account the inner dimensions and the outer dimensions, so that's possible. And again, if it's some other shape, all you have to do is figure out geometrically what that is, take your measurements, and everything will work out just fine. You find your areas, you find your volumes, and you'll be good to go. Alright, just having a little fun there. Basically, if you could find the area of this shape and find the height, you multiply those two values and you have found the volume of that space. Alright, so what I want you to do is engage with some of the material. You get lots of very good examples of finding volumes and perimeters and areas, and then you're going to be able to actually apply those. A lot of the ones that I see on the certification exams are these cylinders. So again, if you can remember that pi is 3.14, or look at your data packet, and if you can remember to use the radius and square it, don't forget that. Once you translate it through that height by multiplying by the height, then you're good to go. Just keep your units the same. That's the biggest issue. Keep track of your decimals and keep your units the same.